cannot tell you how excited I am to be here today to talk to you about fireworks. Who likes fireworks? Who likes sirens? Who likes ringing around around like this? Wonderful. Well, there's plenty out to be had. Now we're talking about fireworks today, of course, which means we need to understand how they work. They do many things. They fly up in the air, they explode, they burn, they make color. We're going to go through these things one by one and understand how they work. Now, before I begin, first I want to say that we are sponsored by Chemical Abstract Service. They bring us shows where we can blow stuff up. You guys like when we blow stuff up? Alright, well, we have come to the most blowinest up show that we have. So, congratulations. Now, this, because it is a blowing it up show, whatever that means. Well, you know what it means. It means you blow stuff up. It's simple. It's going to be loud sometimes. That means that sometimes I'm going to have to warn you guys. I'm going to say cover your ears. And the way that I say cover your ears is ears! So that means if I go ears, you're going to cover your ears. Okay. So let's practice that one time. Yes, you do. You have. You have. Only you know. No, everybody. So let's practice that one. 3, 2, 1. Ears! Very good. Now that's not going to happen terribly often. But it will happen. Now, if you don't like explosions, that's perfectly understandable. You may leave between demonstrations right through these doors here. So if you feel uncomfortable, you may do that. Please don't do it during a demonstration, particularly during one of the more 4,000-degree reactions happening on stage, because I don't want anyone to get set on fire or anything like that. So if something's blowing up here, don't be near it. Everybody got it so far? Yeah. All right, wonderful. Now, we got our safety stuff out of the way. Let's start the show. Now, I said fireworks do many things. They're going to fly up in the air. First of all, let's talk about that. So if you have fireworks flying up in the air, what else can you think of that flies up in the air that maybe NASA would use? What would you call that? A rocket. That's right. Now, rockets and fireworks both burn things to create pressure, to create fire that launches them into the air. Now for us, we're not going to burn anything, but we are going to use something that's really big and forces its way out of an object. And we have a very scientific rocket for you, and that is our plastic bomb. Oh, I got a gasp for the plastic bomb. Fantastic. Now, if we're going to launch that plastic bottle, we need something that is going to expand. And what I have here that expands is probably the coldest stuff that you have ever seen, some of the coldest stuff available on our entire planet. Does anybody know what it's called? Liquid nitrogen. That's very good. I'm going to pour some of it out here. Very careful not to spill any. Make sure I got it good. Now, this liquid nitrogen is very, very cold. I want everybody to look around your face right now. Do you see all the nitrogen in the air? No, you don't see it because it's too small. It is a gas right now. So, since it's so small, we need to make it cold so it sticks together, and then it becomes a liquid. Right. I have more, don't worry. Now, do you think the floor is wet? Well, let's talk about why it may not be. This liquid nitrogen is so cold. Okay, rewind like 10 seconds. This nitrogen is so cold! Better. It's so cold that it is 320 degrees below 0 Fahrenheit. 320, that's 3 times colder than any place on the entire planet Earth as of right now until the next ice age comes, which could be sooner than later. Now, we have our 320 degree below 0 nitrogen. It is only a liquid when it's 320 below. Is it that cold in this room? Is it that cold on the carpet? No! So as soon as it hits the carpet, it turns back into a gas and goes into our lungs. But that's okay because 80% of the air that you breathe is nitrogen. So we need some more of that nitrogen. An important point about this stuff is that it expands. Now I'm going to pour it into this mug. This mug is, let's say, 1 mug's worth of liquid nitrogen. If I were to take all of the nitrogen produced by this liquid, I would need 800 mugs to hold all of it. It expands 800 times. So I'm going to put some inside of my bottle here. Again, very careful not to spill. I am? Are you sure? All right, now, if it expands 800 times, get 800 times larger inside the bottle, what if I plug it up with a cork? What do you think the cork's going to end up doing? Correct! Good guess. Good thing I gave you time to have a guess. Okay. We'll see it again? All right. The pressure builds up inside, it pushes on the cork, it takes the path of least resistance, and then... Now, we don't have to just put a cork in the bottle. We can also... Well, we can still put a cork in the bottle, but what if we turn it upside down on a cork? What's going to fly off this time? The bottle. We are going to make a rocket, just like our firework is going to be a rocket. But we're not going to burn anything. We're going to use the expanding liquid nitrogen. So I need a countdown. From 5, 4, 3, 2, 1. I planned that. That was awesome. All right. So this bottle has been pretty well used. We launched it into the sky, we used it to launch other things, but what do fireworks do when they get up in the sky? They explode! Now you might be thinking to yourself, he's going to blow up that bottle and it's going to be awesome. No, I'm not going to blow up this bottle. I'm not going to blow up this bottle either. I'm going to blow up this bottle! Alright, now, remember how I said some things are going to be loud? You do, good, you're paying attention. This is going to be the loudest part of the show, and it might be one of the loudest things you've heard indoors, other than that Miley Cyrus concert that you went to. Timely reference, I realize. Now, I don't know what you kids listen to these days, so I'm just going to go with whatever I heard on the news. Okay. New Kids on the Block is back, by the way. So, my bottle, and I'm going to put some liquid nitrogen inside the bottle. Now, before I launched the bottle into the sky because I put it on a cork is not the same as a cap. What if I put a cap on here and hold all the pressure inside? What will the bottle end up doing? It will explode. That's right, just like a firework. Now we're going to pour this very carefully in here. Okay. Now my bottle has a lot of nitrogen in it. Now it's not full up all the way. But if this nitrogen gets 800 times larger, do you think I need very much of it? No, I don't. Come on. What are you talking about? No. Okay. Now I'm going to go up here. My foot's super cold now. So I poured nitrogen all over it. I guess that's cause and effect. Now, I'm going to drop it into here. It's going to get dark for a second. It's going to be loud. So this is a good time to cover our ears. Keep those ears covered until the explosion is done. That's what the bottle looks like. Okay. So we have successfully created an explosion, because if you want to make an explosion really simple to understand, it's basically when something small gets really big, really fast. So we have our explosion. Now, I mentioned that nitrogen was not in any way combustible. It did not burn. We need to make something that burns. Now we're going to get to that in 1 second. I need everybody to listen up for a second, because this is important. I need some volunteers. I need 3 volunteers who want to do a little play acting. A little play acting. How about you right here with the butterfly shirt? How about young lady right there? And how about you say the English? Come on now. Let's hear from our great volunteer. That's exactly what I need. Now, what is your name? Everybody say hi, Sarah. Everybody say hi, Adam. Hi. Say it again. Everybody say hi, Tori. Hi. All right, Tori, Adam, and Sarah, correct? All right. I instantly forgot that as soon as I said it. Okay. So, whatever your names are. You are going to play the role of different elements. You are going to be iron. Actually, no, sorry, you're gonna be iron. You're gonna be oxygen. Okay? No, I got that wrong. You're iron, you're oxygen. You're Sarah. So iron, oxygen, you're aluminum, okay? Okay. Oh, you don't want to be aluminum? Well, that's tough. Okay. Aluminum, oxygen, and iron. Those are 3 elements. Now, it just so happens that when you take iron and you take oxygen and you put them together, you get iron oxide. So we have iron oxide here. They're a happy couple and they're getting along really well. They're going to link arms together. They're going to do a little stroll through the park like that. So aluminum, come on over here because your time's coming. Iron oxide. What's another name for iron oxide, those who are aware? Rust. Now you guys are a little rusty. Okay? Now we have this couple. It takes a lot of energy to keep that bond. Iron and oxygen don't bond really, really well. It takes a lot of energy. Aluminum over here bonds with oxygen very, very easily. It doesn't take much energy. So if you introduce a spark between them, it breaks this bond, and boom! And now we have a new bond, and we have aluminum oxide. Now all of this energy that got released makes iron very sad. It makes iron about 4,000 degrees, and iron melts to the ground. Iron melts to the ground. Iron squats onto the ground because it doesn't know how to melt. Let me hear it for my wonderful volunteers. As soon as I remembered what the elements were, that was great. Okay. Now what we just simulated for you all was a thermite reaction. Thermite is a very special blend of rust and aluminum powder. And you might be thinking to yourself, he's not going to create a thermite reaction on stage, is he? That sounds horribly dangerous. Well, of course I am. And I have it right in here. Now, obviously, nobody needs any kind of special clothing for this or anything. Don't have to worry about anything like that. It's just going to make a whole bunch of radiation. It's not going to be a big deal. Nobody needs any special jackets or gloves or helmets or anything like that. Oh, I brought this from home. I'll put that on in a second. Now, I said radiation. That is not the same as radioactivity. This is not what you get from radium or uranium or something like that. We talk more about radioactivity in the fall in our Marie Curie Live show. I'll tell you, the reviews have been glowing so far. Now, we are going to create radiation, which is just another name for light. Now, this is going to give off an extreme amount of light, most of which you're going to be able to see, but there is also light that you won't be able to see. So, this is the time that it's very important that if you're in the front row, you just stay right where you are. You are perfectly safe. No one is in any kind of danger, so don't worry about that. I'm wearing this very stylish, ill-fitting outfit because I'm going to be right next to it, and I don't want to endanger myself on behalf of science. Usually I would, but not today. Now, there's a special way that we light this thermite. And part of it involves the stage moving on its own. So, just gonna ask that to stop for a second, and we're gonna make that work. Now, the way that we make this work is with a blowtorch, assuming that it works. Okay, yeah. Now, the way we're going to light it is with a sparkler, with a blowtorch. So basically you're going to see me get up here and light a sparkler, and then go, yay, thermite, yay, thermite, yay! Think that's how I'm going to light the thermite? No, because that's stupid. I'm not going to do that. I'm going to use an industrial sparkler. You notice this is much larger. This is specifically called a thermite lighting sparkler. What do you think that's used for? That's right. For parties, exactly. Okay. Now, I'm going to put on my special gloves, and what outfit would be complete without this big, ridiculous helmet? All right. I'm going to bring the lights down a bit. Okay. We're going to see our thermite Thermite reaction. Now we're going to be separating the iron and the oxygen. Okay. That oxygen is going to bond with the aluminum. We are going to create an extreme amount of heat and light. We have our thermite reaction. And I always like to roast marshmallows over molten iron. It's always good to have a little bit of ferrous materials in your diet every once in a while. Good. So, how hot do you think that was? 4,000 degrees to melt that iron. Very, very hot, and it's still glowing. Now that is what is used generally in fireworks because it provides its own oxygen. Now without oxygen, you don't have fire. So, definitely has to provide its own oxygen when it moves over to the aluminum. Now, what color was that? Yellow. It's kind of whitish yellow, right? And that marshmallow has seen better days. It wasn't very colorful. So we need to add some color. And the way we do that is to use different chemicals that burn at different colors. And that's not going to stay where I want it to. So, stop. Okay. Marshmallow smells good? Yeah. Well, don't need it. Now I have 3 different chemicals here. This bowl has nothing in it because I'm going to spray pure ethanol into it. Ethanol burns very, very well. In here I have something called lithium, which will burn red, and over here I have something called boron, which burns green. Now all I have to do, goggles for safety of course, so bring the lights down a little bit again. We're going to see, when we combust these different materials, that they give off different colors. So what color do you see there? Blue, that is the ethanol burning. What color do we see here? Red. And what color do we see here? Green. Very good. Now these brightly colored flames are what we would find inside of the fireworks. So when it flies up into the air and explodes in all of its glory, we get to see these different colors. So I'm going to put these out real quick. Turn the lights back on. So we've talked about launching fireworks. We've talked about exploding fireworks. And we have talked about colors in fireworks. I would say that it is time for us to combine all of those together in one grand explosive finale. What do you guys think? Now you notice behind me, 3 balloons of multiple colors. They have different chemicals inside of them. They don't have the chemicals that we had on the table. Different chemicals for similar colors. Now in the, I had red, green color, but I'll give you a second. That's red, right? Yeah, sure, why not? Okay. In the red one we have something called strontium. In the purple one we have something called potassium. And in the green one we have something called barium. Now strontium, you would find it in a road flare. It creates that red light. Potassium, what do you usually find in potassium inside of it? Bananas, right? Different kinds of fruit. And barium, you would, well, if you know anything about barium, you know that often its results can be explosive. So, we're going to use barium to create a color of light. Now with the red balloon, what do you think strontium is going to be? What color is it going to be? Red. And the purple? Purple. And the green? Green. That's right, chartreuse. That's exactly right. No, it's going to be green. Now I'm going to explode these balloons one by one, but first we need to talk about exactly why they are floating. What kind of gas do you think is inside of them to make them float? Helium is almost correct. Now helium is what we call inert. It does not burn, it does not react to other elements, it's very stable. What is the other H element that will burn? Hydrogen. Hydrogen, think back to the Hindenburg. It's going to kind of be like that, kind of like half of the show was in the middle there when I forgot what iron was. Okay, that wasn't too good either. Okay, cool. Now, we have our balloons. I am going to light these with a sparkler, but it's going to be a regular sparkler, but it's okay, because you're going to see giant fireballs. You guys like fireballs? Alright. Now, hydrogen is in the balloons. I mentioned another gas you have to have for a fire. What is that gas? It starts with O. Oxygen. If you take a tidal wave of water. So I want everybody to put on their umbrella hats that they have under their seats. Check really, really well. Don't just look once, look several times. Oh, I knew I forgot to do something. I forgot to give you your umbrella hats. Well, that's okay, because I'm going to have somebody take care of this ring. I need you to do me a favor. Could you hold this to make sure everybody stays dry? Hold up real high. All right, high. Don't put me near a camera because I will do that every time. I'll tell you what, since you guys don't have umbrella hats, I'm going to just, in the show of solidarity, not wear mine either. Now this will be somewhat loud. Usually when you make big, great balls of fire, then you're going to get a pretty loud noise. So this is going to be an ears moment. You don't have to cover them yet, but when I say ears, I want you to cover them. I'm going to cover my ears with these because I'm going to be holding them and stuff. So we're going to bring the lights down a bit. I should probably not stumble around in the dark, so I'm just going to get this stuff out. Now we're going to bring the lights down. I'm going to give you a 3, 2, 1 before I explode each of the balloons. And we're going to see these firework colors in action. Awesome. Yeah. All right. 3, 2, 1. Barrier. 3, 2, 1. Potassium. And 3, 2, 1. Strontium. There was water, but was it liquid water? No, it got in the fire, it turned to a water vapor. So now you are breathing the result of our explosive experiment. So I feel like we understand how fireworks now a little better. Did you guys have a good time?